We present our work, Social Motion Prediction with Cognitive Hierarchies at NeurIP's 2023. In this paper, we introduce a new dataset, a novel formulation, and a cognition-inspired framework for the multi-person motion prediction problem. Given past motions of a group of interacting people, the multi-person motion prediction problem aims to predict their collective future motion. To foster research in this field, we introduced the 5-4 basketball training dataset, featuring professional basketball athletes performing 3-on-2 drills. The 3 offensive players pass the ball while they compete against 2 defensive players who strive for steals and deflections. Our dataset contains intense and strategic multi-person interactions. Here are some example motion sequences. On the left, the offensive players execute a sequence of successful passes. On the right, player Brown makes a jumping motion while defending, and player Purple nearly falls to the ground to make a catch. In addition to regular actions, there are many deception moves in our dataset. On the left, multiple successful fake passes are implemented. At the end of the video on the right, however, a fake pass is seen through and blocked. These cases indicate strong strategic interactions between the offense and defense sides. We note that individuals implicitly plan their actions based on their predictions of others' likely actions. Meanwhile, others engage in similar decision-making processes from their perspectives. By recursively considering these reasoning steps, we deduce that a level K agent acts based on the actions of a level K-1 agent. In light of this, we develop a hierarchical multi-agent reinforcement learning framework and learn agent policies from real-world expert demonstrations. Next, we present some results predicted by our method, with color green indicating input motion. In this case, both player Brown and player Orange succeed in spotting the passing move and approach the offense players accordingly, which is consistent with the ground truth. In this case, player Brown in the left video approaches player Blue to defend. On the right, however, player Brown successfully steals the ball halfway. Though player Brown in 2 videos shows different responses to the passing event, our model precisely perceives the passing move implemented between player Blue and Purple. Given no future information, player Brown naturally executes a strategy by approaching player Blue for a better close-range defense. We consider our prediction results plausible because both our results and ground truth are possible in the real world. Furthermore, we visualize the actions produced by the intermediate policy networks to interpret the recursive decision-making process. At level 1, player Purple makes a passing move towards player Blue based on the historical motion trend. Accordingly, on the second level, player Brown generates the stealing action and causes a defense gap between player Blue and Cyan. Therefore, at the third level, player Orange turns around and steps into the middle of player Blue and Cyan to fill the gap. As a matter of fact, the level 3 actions are closer to the expert demonstrations. Here we present another example. At level 1, player Purple makes a reception and a passing move. Thus, as a defender, player Brown generates the action to turn to player Purple at level 2. His teammate, player Orange, is also getting closer to player Purple to defend. In light of this, at level 3, player Orange chooses a different action, turning to player Cyan. The level 3 actions are also closer to ground truth in this case. From these 2 examples, we can see that our cognitive hierarchy-based model iteratively refines the action predictions, producing not only accurate final predictions, but also an interpretable decision-making process. Thank you for watching. For details of our dataset and method, please refer to our paper.